Hey guys, it's Sadiya here at the Math Center. In this video, I'm going to be showing you guys how to use L'Hopital's rule to evaluate the limit of certain functions. So if we have the limit as x approaches some number of some function being divided by another function, and if that equals either 0 divided by 0 or infinity divided by infinity, plus or minus. These are indeterminate forms. So L'Hopital's rule states that the limit of our function is equal to the limit of the derivative of the numerator and the divided by the derivative of the denominator. So these are two of the indeterminate forms. There are other indeterminate forms, which are so if we have one of these indeterminate forms, then we have to transform our function into a fraction in order to apply L'Hopital's rule. So let's do some problems. So if we have this problem, the limit as x approaches 1 of this function. So the first step is to plug in 1, and then we would get 5 minus 3 minus 2 divided by 7 minus 1 minus 6, and that is equal to 0 divided by 0. So this is an indeterminate form, therefore we can apply L'Hopital's rule. So the derivative of the top is 15t squared minus 6t. The derivative of the denominator is -1 minus 12t. And here we're taking the derivative of the top and the bottom separately, so don't get this confused with the quotient rule. So now, plugging in 1, we would get 15 minus 6 divided by -1 minus 12, and that equals 9 divided by -13. And that would be our limit of this function. So here's another function. So the limit as x approaches 0 from the right side of x times natural log x. So you notice that this is not in a fraction, so if this is an indeterminate form, we would have to transform it into a fraction to apply L'Hopital's rule. So let's first just plug in 0. We would get 0 times natural log 0, and the natural log graph looks like this. So as x approaches 0 from the right side, natural log x approaches negative infinity. So we would get 0 times negative infinity, and that is one of the indeterminate forms that we had. So we need to make this into a fraction. So to do that, I'm going to rewrite this x as 1 divided by 1 divided by x, which is equal to 1 divided by x to the -1 power. So putting it all together, we get this. So now let's go ahead and plug 0 back in, just to make sure it's still in an indeterminate form. We would get natural log 0 divided by 1 divided by 0, which is equal to infinity over infinity. We say 1 divided by 0 is infinity. So now we can apply L'Hopital's rule. So the derivative of natural log is just 1 over x, and the derivative of x to the negative 1 power is negative x to the negative 2 power. We can rewrite that as this, and that simplifies to so now plugging in 0 for x, we would get that our limit equals 0. So that's the answer for this problem. So here's another problem. The limit as x approaches infinity of x minus natural log x. Plugging in infinity for x, we get infinity minus natural log of infinity, which equals infinity minus infinity. And this is an indeterminate form, so we need to make this into a fraction. To do that, I'm going to say that x equals natural log e to the x power. Since these two are inverses of each other, they will cancel out and it equals x. So I'm going to substitute this in for x. So using log rules, we can combine this as one fraction since we're subtracting two natural logs. And it would become this. And to take the limit, we would rewrite it like this. So we just move the limit notation inside the natural log. And so now if we plug in infinity for our x's, we will get natural log of e to the infinity divided by infinity. And this right here is another indeterminate form. Therefore, now we can finally apply L'Hopital's rule to this problem. So we're going to go back to this step. The derivative of e to the x is just e to the x. The derivative of x is just 1. So now if we plug in infinity, we would end up with natural log e to the infinity power. And e to the infinity is infinity, so we're left with natural log of infinity, which equals infinity. Therefore, the limit does not exist.